So boys and girls, hello and welcome to the 16th lecture of this course, which is chemistry, and the code of this particular course is CH101 for the odd semester and CH201 for the even semester, right? And this is Jeet. You are watching the second part of real gases, that is part 2 of real gases, right? So welcome again to the part 2 of the real gases, and in this particular lecture we are going to see multiple things. That multiple things are nothing but Vanderwaals constants A and B, different forms of Vanderwaals equation, boils temperature, Charles pressure, not Charles, it's critical temperature, critical pressure, critical volume, and molar heat capacity of ideal gases. Okay, let's check what we are. Okay, so it starts beautifully with the Vanderwaals constants A and B, and as you people can see that some salient features are, for a given gas, A is always greater than B. The gas having higher value of A can be liquefied easily, like H2NN2. Units of A equals to 2 liter per atm per mole, and that of B is liter mole inverse. Okay, these are the units. Numerical values of A and B are in the order of this and this respectively, and brighter higher is the value of A in a given gas, easy is the liquefaction of that particular gas. Okay, this was the saline features of the Vanderwaals constants A and B that we people have clearly seen. So it's quite easy, don't be bothered, don't be worried. Right, now what we are having different forms of Vanderwaals equation. So at low pressure, what will happen? P will be large, P is negligible in comparison with B. Vanderwaals equation will be reduced to P plus A by V square, P equals to R T. P plus A by V at T. Okay, these are the three options that whenever we do shopping we go for options. So these are the options, right? The accounts for the dip in PV or PV isotherm is at low pressures. Okay, let's see. At fairly high pressure, what we are having, A by V square may be neglected. Vanderwaals equation becomes V. PV minus V equals to RT, or PV minus V equals to RT, or PV equals to RT plus PV, or PV greater than RT, right? So you can see the PV versus P graphs are given here. PV versus Z graphs are given here, right? At fairly low pressures, at very low pressures, P becomes so large that both B and A by V becomes negligible. Vanderwaals equation reduces to P equals to N. So under high pressure, this type of thing happens, that Vanderwaals equation gets reduced to PV equals to N. Okay. Okay, hydrogen and helium people are having. So what is hydrogen, what is helium? Let us see. So these are nothing but the two lightest gases, the most lightest gases, and they are having very small masses. Attraction force are very small. A by V square is negligible at ordinary temperatures. This PVRT, the equation becomes quantitatively observed behavior for real gas, and it is an improvement over the ideal gas equation, Vanderwaals equation for behavior of real gases. Basically, hydrogen and helium, as due to their unique property of being single, having very small size, and all, they have been used as volunteers for this particular equation, right? At low pressure, the gas equation is written as this and this. Z is compressibility factor. We already know value of lower pressure is less than 1. Decreases with increase of P for an given value. Z has more value for higher temperature. Okay. And at high pressure, what happens? Vm minus B RT. This common expressions are coming. Here the compressibility factor increases with increase in pressure at constant temperature, decreases with decrease in temperature. This is quite important message, that the compressibility factor increases of pressure of constant temperature, decreases with increase of temperature at constant temperature. For the gases H2 and He, above here is observed, right? So basically H2 and He were taken as volunteers, served as the subject material for the conduction of this particular test. Now we can see we are having the boils temperature, critical temperature, critical pressure, critical volume. So what is boils temperature? You see the temperature at which real gas obey the ideal gas equation. It's called boils temperature. Gases liquefy at boils temperature is 46 Kelvin, or they may liquefy at a much lower boil temperature, that is 26 Kelvin. Okay. Boils temperature, the formula is A by RB equals to half T1, Ti, not T1, Ti we can write, K is inversion Vanderwaals constants. Okay. Critical temperature is there. It is the maximum temperature at the gas at which the gas can be liquefied. The temperature above which gas cannot exist as liquid. Formula is T equals to 8A by 27 RB. 27 RB I have seen somewhere. Okay, fine. Critical pressure is minimum pressure required for liquefaction, A by 27 B square, and last one is volume occupied by 1 mole of gas at Tc and Tc. Okay, most simplest formula, V equals to 3B. Now this is one graph having boils temperature and compressibility factor, right? And it is showing that the hydrogen and helium are having different type of slope and others are having different type of slope. Okay, that's how it is. So next topic is molar heat capacity of ideal gases. Now, as we people know, specific heat of a substance is defined as the amount of heat required to reach the temperature. We know this thing, I'm not saying it again. The amount of specific heat calorie is this, and 1 calorie is defined as the amount of heat required to reach by of 1 gram of water by 1 degree. 10 C 1 degree. Molar heat capacity is defined in terms of same thing in terms of mole. Okay. Now this is the relation. This is important. This is the relation between molar heat capacity and specific molecular weight. Okay. For gases, there are two values. That is molar heat of constant pressure and constant heat, and constant molar heat at constant volume. Okay. Cp is greater than Cv. Already these have been discussed. We have derived also the ratio of Cp and Cv. Is like the Cp equals to 5, Cv equals to 3. Okay. Gradually, if this type of level comes, then definitely Ri is getting ready for us. So what we are having for diatomic gases, Cp is equal to 7 and Cv is equal to 5. So this type of Poisson's ratio we people are getting. Okay, if the value is altered, then this type of ratio will be getting. The Cp and Cv are basically the specific heats, and I'm not discussing here again because Cp and Cv are the most common things that we people have studied in thermodynamics. Okay. right? So that's how it is about CP and CV, and M is molecular weight, everybody knows. Okay. So this was all about the things that we are having inside the real gas part, and in these two lectures we have clearly seen that, starting from ideal gases, that why ideal gases are called ideal gases, why they obey certain rules and regulation, and why other gases does not obey. Now if they obey, what are the laws they obey, and under that condition what are the different aspects they are having. Then we have seen what is the kinetic theory of gas, right? And we have not seen the details of kinetic theory, but we have seen some major points of kinetic theory of gas which is needed for us. Okay. Now after that we have come across the corrections of pressure and volume. And gradually we have discovered the Vanderwaals equation of gas. This was for the last lecture, and in this lecture we have come across different types of Wales temperature and molar heat capacity of ideal gas and critical volume, critical pressure, and all, right? So these were the details about real gases that we are having in the BTech syllabus. So with this, the physical chemistry module has also ended, and this lecture will be followed by certain questions. Try to answer the questions. In case of any problem, just contact me. Okay. So thank you so much. We'll meet again in the organic class. So till then, be ready, and thank you and stay safe. Okay. See you in the next class.